Okay, so we're going to work on a few example problems involving limits. First one is going to be asking us to, we're estimating a limit numerically. Now we have this really kind of odd looking function here, and it's really difficult for us to deal with normally, but if we were to try to just figure this out numerically, it's not quite as hard. It's just kind of a little bit more labor intensive. Um, but what we're going to do is we're going to set up a structure, right? So we have x, and we're going to have f of x, and we're going to make it kind of a little table. Okay, so main idea here is that in the middle, we are going to have where our limit is, it's our limit as x approaches 0. So we're going to have 0. This is what we're trying to figure out. And we're going to try to figure this out based on a pattern of numbers coming from the left, or coming from the right and the left. Okay, so we're trying to pick numbers that are close to 0. So if I were to plug in, let's say, any number that's very much smaller than 0. So if I did like negative 0.01, or the same thing as negative 1 over 100, what happens if I plug it into that function? Well, if I use my calculator and plug it in and make sure that I use brackets and everything correctly, I'm going to see that I get 1.995. Okay, 1.995. Now, from the other direction, let's say I chose instead of negative 0.01, I pick a positive 0.01. Well, what answer am I going to get here? Well, if I plug that in, if I plug in 100th in, I'm going to get 2.05. Right, around 2.05 or 2.005. So pretty close to the exact, pretty close. Now, my numbers are coming in a logical way from this side. My numbers are coming in a logical way from this side. So what would you expect to be in the middle? That is how we deal with limits. What is the predicted number? And here you should see that it's going to be 2. So if you're trying to evaluate a limit numerically, you're looking at what number should go in the middle? What would I predict to go in there? That's what a limit is. It has nothing to do with what the function is at, at 0. It's what the function is you would predict based on what's going on around it. Second example is finding a limit. Okay, so we're finding the limit as x approaches 2, where f is defined in the following way. So we're looking at as x approaches 2. So this function is 1 when x isn't 2, and 0 when x is 2. So let's think about this in a couple ways. Let's make a table. And let's make a graph. So our table is going to look something like this. Now, let's do several points. So we're looking at at 2. So let's look at the points 1, 2, 3, 4, and 5. Well, x is going to be 1 for every point except for 2. Now, just looking at it this way, what number would you expect? If this is a 1, and this is a 1, and this is a 1, and this is a 1, you would expect a 1 to go in there. But that's not the case here, right? It's actually a 0. So this this doesn't matter. The fact that this is a 0 doesn't matter. It's the fact that we can predict based on left and right what it should be. Okay? The fact that it's a 0 does not matter. If we graph it, we can see this in another way. Okay, so if we graph all points except for at 2, which is right here, we have this nice easy graph. We have this hole here because at 2 our graph has a value of 0. So you can see that it just jumps down there. The fact that this graph is entirely predictable except for this point, okay, and that point is missing, even though that point is down here, we still say that the limit of f of x as x approaches 2, we're going to say that that equals 1 because the function approaches that point from the left and right. So think about it as, if I didn't know that that point was there, right? If I didn't know, and somebody just, it was empty, and somebody just said, okay, well, I'm traveling along here, and I've gone backwards to it as well. As long as you're pointing in the same direction, it doesn't matter what the function actually is, right? It doesn't matter that it's 0. It matters that from each side, it looks like it's going to be 1. Okay, so we just call it 1. Right? That's what a limit does. So example 3, so behavior that differs from the left and right. So in the previous one, we had the same behavior from left and right. Well, what happens if we have different behavior? So this graph here, this is an interesting one. The absolute value of x over x as x approaches 0. So let's draw this graph real quick. So we got y and we got x. So, okay, and we can also make a little chart to help us. May make one more. 1, 2, 3. Okay, so if we're looking at the point around 0, so we'll say 0's here, and we're going to have -1, -2, we're going to have 1, we're going to have 2. Okay, so here we go. So if I were to plug in these numbers, so if I plugged in -2, so the absolute value of -2 over -2, that's 2 over -2, which gives me -1. If I do the same thing for -1, I'm going to get the absolute value of -1 over -1, which gives me 1 over -1, which gives me -1. Lots of -1s. Okay. We can't plug in 0 because it doesn't work, right? We can't divide by 0. That's not in our domain. So there's really no value here. Doesn't mean that it can't have a limit, though. So let's look on the other side. So if we plug in 1, the absolute value of 1 over 1, it's easy enough, is 1 over 1, which is just 1. And if we do 2, the absolute value of 2 over 2, again, this is just going to be 1. So what we see here is that from the left of 0, we look like we're -1. And from the right of 0, we look like we're +1. So you may be asking yourself, okay, well, this is kind of a weird graph. Well, the limit exists everywhere except for here. And the reason behind this is that because it's not predictable, right? If you were coming from the left, you'd be like, okay, well, I should be going towards -1. But if I'm coming from the right, I should be going toward 1. So because these don't agree, because they don't agree, the limit does not exist. And that's because from one side is different. The behavior from one side is different from the other. So unbounded behavior. So discuss the existence of this limit. Okay, so this one I'm just going to graph and kind of explain how this looks. So draw our axes here. We got y, we got x. And we have before looked at this graph. This is like a rational graph, or it's like a rational function. Remember, rational functions kind of have this bowed shape, but because this is squared, instead of this part being down here, it's going to be up here. So this is what a 1 over x squared graph looks like. Okay, so this is very important. Okay, for 1 over x squared, as we get closer and closer to 0, right, we're not allowed to be 0, right, because x squared cannot be 0, therefore x cannot be 0. The fact that x can't exist at 0 does not affect the limit. What does is the fact that as x goes to 0 from each side, we're going up towards infinity, right? We're dividing 1 by a really, really tiny number. So if you imagine like 1 divided by 1/10 is 10. 1 divided by 1 over 100 is 100. 1 divided by 1 over 1,000 is 1,000, right? The closer we get to 0, dividing by a smaller and smaller number, the larger and larger our actual function values getting. So you can see that if I make that number as small as possible, I'm going to have a number very close to infinity. So because even though they go to the same spot from left and right, because that is not a real number, because it's infinity, the limit doesn't exist. So this limit does not exist because from left and right of 0, the function does not approach the same real number. So that's this one does not exist because it needs to approach a real number, and this, as you can see, is just skyrocketing off into infinity. Our last one here is talking about oscillating behavior. So discuss the existence of this limit, right? So sometimes when we oscillate between different points, which oscillation is just kind of bouncing back and forth, we end up with where the limits can't exist. Okay, so for this one, so the sine of 1 over x. So this one's kind of a difficult one to think about. So last time we just looked at 1 over x. Just think about 1 over x for a second. As x gets smaller, so let's say, remember we did this last time, so 1 over 10, or excuse me, 1 over 1 over 10 is 10. 1 over 1 over 100 is 100. 1 over 1 over 1,000 is 1,000. Right? So as we get smaller, the other side gets bigger. And so what happens here is, and we know that because we're plugging this into sine, we're talking about angles. Okay? So we know how our sine function goes, right? Sine function looks something like this. That's just the sine of x. X goes up rather normally. Well, what happens is that as we get closer and closer to 0, right, that we're growing our angle by times of 10. So it's like it's starting to accelerate. So instead of having this nice smooth curve throughout, what happens is as we move along, it's progressively getting 10 times more frequent. So what it's going to look like is this. So I start speeding up, and I start speeding up, I start speeding up, start speeding up, start speeding up, and then it starts getting real crazy at the end. And so what you'll see is it gets right close, and then it kind of speeds off again. It's hard for me to draw this, I apologize. But what's happening is that when this is getting around 0, this angle is so huge, and it's moving, and it's gaining value so fast that it's impossible to tell where it's going to end up and what's going to be in the middle. So because we don't know what angle we're approaching, because we can't comment about the angle 1 over x around 0, this limit does not exist. This is kind of a strange one, but basically there are 3 ways a limit is not going to exist. One, if it differs from left to right. one, if it's unbounded from left and right, and lastly, if it oscillates between 2 points that we can't tell what they are.